Hello, everybody. Welcome back again to the second talk of the afternoon program. Right now, we have two speakers lined up for you. It's going to be Alexander and Tygo, and they will tell you something about how football is very complicated and has a lot of complex data, but these guys are here to make your life easier with that. So I'll give them the floor.
That's always a great catch. Thank you. Thanks for being here, and thanks for inviting me to give this talk. My name is Alexander. I'm a PhD student at the University of Groningen and also a data and innovation analyst at Feyenoord. Today's talk will be primarily about DataBallPy, an open source package developed for soccer analytics. And in the second half, Tygo will take over and he will show a practical application of how DataBallPy was used within the Royal Belgian Football Association for deep dive analysis into pressing. But first of all, what is DataBallPy? DataBallPy, as I said, is an open source Python package, and it's primarily developed for soccer analytics in the tactical sense and the contextualized sense. It is aimed to really quick start your analysis. So every analyst has their own questions, and that will always stay that way. DataBallPy is not here to answer all those questions, to be able to do all your analysis for you, but it does deliver a very unique structure, especially developed for contextualized and tactical analysis. So that is what DataBallPy primarily has to offer, and will make any further analysis easier for you to do. Now, before diving into the structure, I will quickly point out the different kind of data sources that we have. If it works. The first one is event data. Event data actually captures what happened. So it captures the event happening, for instance, a pass, a shot, a dribble, which player was involved, where it happened on the pitch, an associated timestamp. So if you want to know who passed to whom, then you need the event data. Secondly, we have the tracking data. And the tracking data captures where. So it captures the positions of all the players about 25 times per second. And this gives us the possibility to look at movement patterns over time and analyze shapes of teams, as we saw in previous talks as well. Now, the thing we see in literature is that although these data sources individually are already really interesting, combining both of them has added benefit, especially for tactical analysis and for contextualized analysis. The key problem here is synchronization and alignment between the tracking and event data. And to give you an example of what I mean with it and why it might not be as simple as you think, I have a short video clip, and there I can explain you what I mean with the synchronization. Now, in this video clip, we will see 3 passes and 1 header that ends up going to the post. And the goal of the alignment or the synchronization of the tracking and event data is finding the exact frame in the broadcasting or tracking data where the event is actually happening. And the easiest approach to this might be, which all of you probably think about, is timestamps. If both the event and the tracking data have timestamps, we can just minimize the difference between those, and we know when the event happened in the tracking data. Now, to visualize this, I plotted the tracking data on the bottom right, and the tracking data and the broadcasting data as well will stop for 1 second when there was an alignment between the tracking and the event data in terms of timestamps. So that will actually show you what the timestamp thinks that the synchronization, the right match between the frame and the event data is. And what we'll see in this case is that the first 3 passes are synchronized pretty okay. They are pretty short within what you would expect it. But especially the last event, the header, is about 4 to 5 seconds off. So I'll start counting once you see on the tracking data that the event, the header is happening. 1, 2, 3, 4, 5, and this is only the frame where it thinks the header is happening according to a timestamp alignment. So we can see it's 4 to 5 seconds off to what we would actually expect it. Now, if we were to do some tactical analysis in terms of expected goals on this, we have a first key problem, and that is, do we take the player position at this frame or the ball position? The player currently is standing basically at the goal line, and therefore an expected goal value of a header of about 35% is really high, because when you're standing at the goal line, there are high chances of you scoring. But for this location of the ball, we see actually that the expected goal is very low. And this is primarily because there's a poor synchronization. They are not at the same location, what you would expect. Now, from this, we can already conclude 2 things. First one, the timestamp synchronization is not really reliable, and that's primarily because there's not only a standard offset between the timestamps in the tracking and the event data, but also a random component in that. And that's not only what we found in our analysis, but also in the literature, we found that there's a standard deviation of about 4 seconds between the tracking and event data timestamps of what is expected to be the right alignment. So we solved this within DataBallPy, and the synchronization in here, you will see that now the passes are slightly better aligned, but especially the header is way closer to the frame where you would actually expect the header to happen according to, well, the common knowledge you have and also the video data you see. It's now within 1 frame of when the ball actually touches the head of the player according to the broadcasting data. I will not tell you exactly how this synchronization algorithm works. First thing I wanted to point out, I see right now, is that right now the ball and the player are approximately at the same location, and it means that the tactical analysis, in this case, the expected goal value for both the player and the ball will be the same and also a lot closer of what you would expect. Now, I explained the synchronization algorithm at a previous congress, the MatSport conference previously this year. So if you want to have more information about how the algorithm works, there's a proceedings paper you can read, and also there's a lot of documentation of DataBallPy that explains the synchronization algorithm. What I do think is more interesting for you guys is to get to know how you can use it in your own work. To do that, you first need to load in a DataBallPy game object. Everything within DataBallPy is surrounded around the game object. And there are basically 3 ways to do that. Of course, if you have your own data, you can always work at that. But because of the group of Manuel Besek and his team, they introduced an open data set of tracking and event data. So if you use the get open game function from DataBallPy, you can always also load a game object with both tracking data and event data and still do all of your analysis, even if you don't have access to data yourself. If you work within a federation or professional soccer club, chances are you have your own data, and therefore you can also work with that. DataBallPy offers support for different data providers, among which TraceCap, Opta, StatsBomb, and many more. So if DataBallPy supports your data provider, the only thing you have to do is click through the slides. Yes, is use the get game function from DataBallPy, and you can add your data as inputs to the get game function. It will actually load in a DataBallPy game object. Now, the last option is if DataBallPy doesn't support your data providers, we can still use Kloppy. And I think Kloppy is known by many of you, but Kloppy has the widest support of different data providers in soccer data. So you can always load an event and or tracking data set from Kloppy and transform it to a DataBallPy game object. So any further analysis you can still do within DataBallPy. Now, once you have loaded in your game object, in this case the open game, for which you don't need any data yourself, the only thing you have to run is the synchronize tracking and event data method that is built on top of the game object. And within a few seconds, it will create a mapping between the tracking data frames and the event IDs of that specific match. And there you have the state-of-the-art synchronization algorithm within an open source Python package that's really easy to use. Now, this is already a great starting place for any analyst to work, because right now we have all the information of a single game at one place. It's all built in the game object. Here we have the event data, the tracking data, and extra metadata. Secondly, everything within the game object is standardized. So even if you use a different event or different tracking data provider later on, it all will look the same within the game object, and you can continue with that. The third point is the synchronization. I already pointed this out, but this is especially important for contextualized tactical analysis. The fourth one is everything within the DataBallPy game object is built on top of pandas data frames. So if you know how to work with pandas, you already know how to work with DataBallPy. Now, the last thing, because everything is in one place and everything is standardized, we can now create and compute extra metrics on top of this. You can do this yourself because it's standardized, because you know how everything looks. But we also computed already quite a few metrics on top of this, which are available for you to use once you use DataBallPy. Now, I will not go through all the different metrics and features we have, because there are quite some. It ranges from filtering data, adding velocity, expected goals, expected threat, different pitch control models. It's all built in already, but most of these are currently scientific papers on their own, so it will take too much time to explain them all in depth. But I will explain a little bit more about what we always want for the features and metrics that we have inside DataBallPy. And the first thing is, it should be really easy to use. So similar as I showed you earlier, but in this case, if you want to compute individual player possession on a frame-by-frame basis, the only thing you have to go is the game.trackingData.add individual player possession. Now this is really easy to use. It's efficiently created, so you can use it. And again, it will create a mapping between the tracking data frames and which player has possession at that frame. Now, the problem with this is it might feel a little bit like the Pythonic magic. You don't really understand what is happening under the hood. So the second thing we always strive for is very clear explanation within our documentations. We have very elaborate documentation on all the features we showed before, not only explaining how you can get the features, but also adding extra text, visualizations, even referring to specific formulas within the scientific papers of how it actually works. So therefore you don't only get to use the feature, but you also know the strengths and the weaknesses of the feature. Now the last thing I want to show you, and I'll touch on this shortly, is the visualization model within DataBallPy. So the one I use the most by far is saving a video of the tracking data and event data together. All the features that I just showed you, you can also visualize over time with the tracking data here. And I use this a lot because it gives us contextualized information about the tactics, about what is happening at the pitch. Now, to give you a very short example, I'll not go through all the code, but with between 10 to 15 lines of code, you can load in a game object, do some pre-processing, have features computed like individual player possession and also pitch control, and save a video of it with all the information you want to see. And that will look something like this. Now, as I said in the beginning, DataBallPy will not be able to do all the analysis for you, simply because always the questions will be different, but it will give you a unique structure which will make it very easy to continue onwards. So to explain that, I think Tygo is the right man to show them how they did.
Yes, thanks Alexander, and hi to everyone again. So my name is Tygo Nikamp. I've been an intern at the Belgian Football Association, and I'm studying sports science at the University of Groningen. And during my internship, I've been working mainly with pressure as a topic, and in doing so, I was challenged to create a pressure dashboard, which turned out to become the pressure pack. Quite cool thing, I'd say myself. I will show you it at the end of the presentation, so stay tuned for that definitely. But first, pressing. Pressure is rising. Yeah, there we are. So efficient pressing as the topic. I've brought two clips with me, so I think we've all got a clear picture in our minds of what efficient pressing looks like in soccer. So the first clip you'll see here is a lot of players moving. Ukraine is pressing Belgium here. There's a lot of external load and distance covered, but Belgium proceeds to play through the Ukrainian defense easily. Unfortunately, it will not end up in a goal or a shot on target or something, but you'll get the idea. And on the other hand, you've got the more efficient pressing, I'd say. It's a bit more tactical way of pressing, trying to cover less distance and close on passing lines, etc. So as you can see over here, the Belgian players are standing quite good, forcing the right back of Ukraine to deliver a pass which is not good enough, and the Belgian team regains possession of the ball. So we sat together and for us looked at what is efficient pressing and how can we quantify this. So it starts with minimizing the energy expenditure and increasing or maximizing the tactical gain. So the idea for us was not to press harder but to press smarter. And before I will go into the analysis itself, I'd like to take one step back to the foundation. So instead of reinventing the wheel at the RBFA, we chose to use existing open source packages such as DataBallPy, which Alexander showed you all about. So the analysis, the synchronization logic, all processing stuff uses code from DataBallPy, which saved us a lot of time doing the tedious coding, which we left to Alexander. And this freed up space to do analysis, which is what we as scientists like to do the most. So you see the common data format in here as well. We did not use DataBallPy 1.1, but we changed it slightly. And for those of you who do not know what the common data format is, it's an initiative by a group of researchers, soccer federations, and universities. And they are for standardization of data in soccer. So those of you working in soccer and working with data know that there are a lot of different input sources from different companies, all with different formats. And the universal DataBallPy common data format solves a lot of problems here. So when doing pressure or research on pressure, you need a model to quantify pressure. And this is where the pressure intensity model by Joris Beckers comes in. I don't know if Joris is here in the room, but yeah, there he is. Thanks, Joris. So I use the pressure intensity model, which captures pressure and turns it into a time to intercept. It's an initially introduced by Spearman for a passing model. And the time to intercept value, it says it in the name, it's about time to intercept. And for now, certain players. And this time to intercept value gets transformed using a logistic transformation into the so-called probability to intercept. And the name says it again. It's about a probability that you will intercept the player. And there's a time threshold here. So it expresses it as a value from 0 to 1. And if it's 1, you will be able to intercept the player within 1.5 seconds. And to get a bit of a feeling by what we mean here, I brought a situation out of real play. So as you can see over here, player 21 is pressing player 2. And so the good thing about the model is that it takes the speed into consideration as well. You can see by the line coming out of player 21 here, he's moving towards player 2, who is moving away from him. And this results in a PDI value of 0.54. And I'd like you to keep in mind these values. Hence, we used it as an input for my pressure model. And as you can see in the back, these values are available for the entire team. For every single frame, we can calculate it. We see some rather high values on the heat map on the matrix as well, which are the sideline. So the sideline can also exert pressure on a player. So when you're moving towards the sideline, you'd receive pressure from the sideline. Hence, we modeled it in. Which brings us to the pressing instance. So for research, we try to extract a clear moment of pressing, which all starts with deliberate possession by the attacking team, meaning that the attacking team must have the ball for 5 seconds, and at least 2 different ball carriers have to be involved. And then for the defending team to count as a pressing instance, there has to be team involvement. So imagine the rare scenario that Lukaku will be pressing on his own really hard. I know it's hard to imagine, but imagine it. Then it would not count as a pressing. There has to be at least 4 players involved. And for one player, the pressing must be oriented at the ball carrier, and the thresholds, the one threshold is higher for this player directed at the ball carrier. And these were the thresholds we saw in the previous slide. And last but not least, we made an addition to the model, an angular constraint. So we saw a scenario where the pressure at the ball carrier, when players would be running alongside each other. And if it would go through. Yeah, there we are. So specific scenarios, mainly fast left and right wingers. For example, Jeremy Doku, he would be running really fast and the defender would try to catch up and would be running parallel, but we would never be able to reach Doku or the ball, but yet the model would attribute quite high PDI values, and we solved this with our angular constraint. So we analyzed 226 matches with this model. The majority came from the Nations League and some games from the World Cup qualifying series as well. And out of these matches, we identified 16,121 pressing instances. And we analyzed these instances. First, we looked at whether they were successful, yes or no. So we looked at what is said about success in defense in literature and sat down with the data analysts from the RBFA to come up with a set of rules. I've written some down here. So when you regain the ball, the pressing has succeeded, which is an obvious one. And for example, when the attacking team manages to shoot on target, the pressing would have failed. And the main variable for analysis, to say something about efficiency, was external load. So for each and every single pressing instance, we extracted an external load profile with metrics like distance, speed, but also speed in different zones, acceleration, and metabolic power zones. We used the functionalities package to derive the metabolic power. And for each and every single external load variable, we calculated a linear mixed model. I don't know how good you are into statistics right now, but it's basically a large model where you can predict an external load variable and you can add in some random factors. So we included the match and team to account for variance there, and the fixed factors success, so was it successful, and block height. And block height is something I have not touched upon yet, but we added it as a context. Hence, pressing is not the same everywhere on the pitch. And we could, with adding block height as a context, we can compare between different pressing situations. So we used the definition by Bauer et al. And it basically classifies block height looking at the center of the defensive unit, which basically is the team minus the goalkeeper. So now the results. I've only brought 2 figures with me here today. We're working on a publication, so I'd say take a look at my LinkedIn afterwards and follow me, and then you'll see once the publication is ready. But as you can see here, for total distance, we found that successful pressings were way shorter, all significant here. Those intervals were rather small, so you could almost not see them here. The effect was largest at high block, meaning that the distance covered at high block and successful pressings was way lower than at failed pressings here. Additionally, successful pressings involved way more accelerations, significant again at mid and high block, and we see here that the effect is again largest at high block, which means that the pressing instances that were successful were briefer and more energetic, and the context here mattered, so we saw that the difference was largest at high block. And I'd like to touch upon the context being important, but first another finding that was quite interesting. Yeah, there we go. So the between team variance turned out to be negligible, which means that there was a high consistency in the external load profiles of pressing at an elite level. And to give a practical example, this tells us that what it takes for a team like Liechtenstein to press successfully is exactly the same external load-wise as what it takes for Spain to press successfully. So no difference in teams here, which is quite interesting, I'd say. Then the context being important. So I'd like to go over a scenario here with you together. Imagine you're a coach and you're keen on pressing play, and you're trying to determine which player you need to opt out of your squad for the next game. So I think we would all agree here that we would leave out player 2. Hence he has covered less total distance and given less accelerations, which is the old-fashioned way of displaying external load metrics. But when we take a look at the situation in its context, tables turn. You'd see that player 2 has covered more distance in pressing and delivered way more accelerations than player 1. So the context in which the external load metrics are unfolding is really important here. Then, last but not least, I promised you something cool at the end, so the pressure pack. We applied the model, and you can easily load in a match by one click. So there we go. And the model provides you an overview of how your team pressed, and you can also select your opponent. So how did your opponent press? We've got normal pressings in here. We tuned the model to capture counter pressings as well. And additionally, you can see the best performing players and the worst performing players during this match. Also, most of you would be familiar with passing networks in soccer. Well, we at the RBFA created a pressing network, which is basically the same as a passing network, then for pressure. So you could easily see once a match is played, which players pressed which players the most. And say, for example, you know that a left center back is weak in build-up play, and you want to tactically pressure this player the most. You could see at the end of the match, analyze whether this tactical choice was executed correctly. Then last but not least, we've also got an individual player page here, so you can get an easy timeline of how did a player perform in pressing. Also a impact score here, which is basically the amount of pressings squared divided by the total amount of pressings to get a feeling of how much did he contribute, but also how well did he contribute. We also have a pressing timeline in here as well, which can be used to compare players within a match. So say you've got two players for rather similar positions, which player pressed the most, but also the same player between matches, or within matches, between matches then, to see did this player press well this game, or did he perform better in the other game. So this was the dashboard I wanted to show you, and I would like to end our talk with a call for more open source coding and context. Yeah, there we go. So thanks for listening to us today. And if there are any questions, we've got about 2 minutes left. So brief questions.
Go to the next slide.
Indeed, thank you guys very much for the interesting talk. Cool to see the package and how to some use cases. And my work has indeed almost been done for me. We have some time for questions. So are there any? Yeah, go ahead.
Thanks for the talk. Beyond like raw numbers, when it comes to pressing, do you also consider whether a player keeps the structure of the team during the press? Because I guess it's also kind of important, right? That you don't want a player to just like run around. You know, you have to keep a certain structure. So I'm wondering if you also like thought about it, and how did you implement it in your model?
Yeah, we did actually. So only players within 20 meters of the ball were taken into consideration for pressing.
That's perfect. Thank you.
Thanks for your presentation. Very clear, even for a non-data scientist. So well done. If we look at the goal why we're doing that, the goal is to give team insight in increasing the number of interceptions, correct? That's why we do this.
Mm-hmm.
So if you look at attacking play, we look at a very important percentage like expected goal rate. Isn't in what you show on the feedback of pressure situations, you show distance covered and so on, but you don't show the number of interceptions. And isn't expected interceptions, for instance, I'm just making it up, isn't that in the end the important and the decisive data insight that you're looking for?
Yeah, great idea. We have not thought about that yet. The first initial idea here was to sketch the external load profile of what it takes for pressing to be efficient. The model is quite new by yours, but this would be a great application for it, I think so. Yeah, indeed.
I think if I may add on that, it's also pressing situations are not really linear in what the outcome is. It's not if you're 80% right, then you also have 80% more interceptions or something. If you're just a little off, then maybe the opponent is getting through it all the time. So linking those kind of metrics together is really difficult and probably needs an extra tactical or contextualized layer before we can actually make links in that aspect.
But that is in the end what you would like to know.
If the goal of the pressing is to create a turnover alone, then that is what the goal. But in practice, we also see that sometimes it's fine if they play back the ball, or sometimes it's fine if they don't get over, they don't get in our final third. And then it gets way more complicated to have like concrete hard metrics, as this also changes over the match. In the beginning, you might want to force a turnover, but in the end of the match, you're fine as long as they don't reach your final third. So then it becomes way more complicated to include everything.
Good point.
There. Thank you.
Thank you for your good questions, and thank you again for the presentation. Also for you, we have the special gift. So I feel like both of you get to have one.
Thank you.
There you go.
Thanks.
Thank you again. And then we'll have a short 15-minute break, go to the toilet, have some coffee, have some tea, and then would love to see you back for the next talk afterwards.